Integration by inspection. So this is the start of our look at how to integrate a load of different types of functions. Obviously, so far from first year content, we've just integrated polynomials, so like x squared, x cubed, and so on. But just like with differentiation, we've learned to differentiate all these new functions. We now want to also learn how we can integrate them. Okay, so it's called integration by inspection, and if you look in the booklet, there's lots of just standard results that we could probably remember. You do get some of them in the formula booklet as well. But let's just sort of have a quick thought about where these come from before we start using them. So let's just think about the knowledge we've got for derivatives. So if we wanted to differentiate an exponential function, we would realise, well, whenever I'm differentiating an exponential, the power stays the same. And I look at my power, and if I differentiate this, I would get 2, so I'd multiply the front by the derivative, which is 2. Sine, we used this a lot, didn't we? So that sine differentiates to cos, so that would be cos of pi x. So with trigonometry, the angle stays the same. And you look at your angle, and then because it's a constant, pi is just a constant times by x, the derivative of this, if you differentiate a number times by x, you're left with just a number, so the derivative would be pi. So we'd multiply the front by the derivative, which would be pi. The ln one was the one that I said was a bit awkward, and we're going to look a lot about this in the next coming sections as well. But when we differentiate a log function, we need to remember it turns into a fraction, and you get the original function on the bottom. The derivative of x is 1, so you get 1 over x on top. Okay, so we can use this knowledge of derivatives to try and sort of see, well, what would the reverse of that be? Okay, so if I was trying to integrate an exponential, then I would say, well, the power stays the same. If I was differentiating this, I would be multiplying by a. What's the inverse of that? You just divide by a, don't you? And obviously we need plus c on these integrals. Okay, so if I was going to integrate 1 over x, well, I know if I differentiate ln x, I get 1 over x. So if I integrate 1 over x, I'd get ln x. Technically ln modulus of x. We'll see more on that later. Cos function. Okay, so if we go clockwise when we differentiate, guess what? Anti-clockwise when we integrate. So cos integrates to positive sine. The angle stays the same. If I was differentiating, I'd be timesing by a, but I'm integrating, so the opposite is to divide by a. Sine, okay, so we're going anti-clockwise because we're integrating. Sine, we go to negative cos. Angle stays the same. Divide by the a, because we are integrating. Last one, sec squared. We did see this. We'll do a lot more on trig in the next couple of weeks. When you differentiate tan, you get sec squared, which is actually the easy way to remember these new trig ratios is the third letter. Because it's sec, it's 1 over cos. Okay, so sec squared is the same as 1 over cos squared. And it's just the third letter tells us that, and it works for each of the new ratios that we're going to look at. But we'll see that later. If we integrate sec squared, we just need to remember that we get tan. Because when you differentiate tan, you can use the quotient rule. You can write it as sine over cos. We did it earlier on. If you differentiate tan, you get sec squared. So if I integrate sec squared, I get tan. Okay. Example 1, we're going to integrate 2 cos x plus 3 over x minus root x with respect to x. First thing I would think about for this is there's actually 3 separate functions that we're trying to integrate. So let's just think about them as 3 separate integrals. Okay. Cos integrates to sine. It's only x as well, so we're going to be dividing by 1. Okay, so that would become 2 is just a constant. Don't do anything with that. Cos integrates to sine. And the coefficient is 1, so if you want, we could divide by 1, but it would stay the same. Okay, 3 over x. I'm going to do a little bit of working out for this one actually. So, you know, I was saying earlier about thinking about it as like separate integrals. I probably should have started by writing this one a little bit differently. Okay, let's split them up as separate integrals. So we're integrating 2 cos x. We're integrating 3 over x. We're also integrating, I'll take the minus outside. No, I'll say it's plus for now. So minus root x with respect to x. So with these integrals, you might not have seen this before. If there's a constant multiple, you can just take it outside the integral. So that'll be the same as integrating 2 times by cos is the same as 2 times by the integral of cos, which I sort of skimmed over earlier. Really important that we actually think about it for this one, because 3 over x is the same as 3 lots of 1 over x. Take that 3 outside. Okay, and the minus, you could also take that minus. Root x, think about index form, sorry. It would be the power of a half. Okay, so now I've written it like this, as these separate integrals. It's a lot easier to manage this question. So the integral of cos is sine, so that we can see now that just becomes 2 sine of x. And again, we divide by 1 if you want to divide by anything. We know the integral of 1 over x is ln x, so that's 3 lots of ln modulus of x, technically when we integrate. Last one, minus, add 1 to the power, so that would be x, it's the power 3 over 2. Divide by the new power, so divide by a fraction, multiply by the reciprocal. Okay. Part B, we've got 2 separate functions. So we're trying to integrate 1 over cos squared and minus 2e to the x. I am going to write this as 2 separate integrals. 1 over cos squared is the same as sec squared x minus 2 lots of the e to the x. I'm going to take the minus 2 outside, and then we're just going to integrate e to the x. Okay. Remember what I said earlier? It's the third letter. So if it's 1 over cos, that's the same as sec. So when we integrate sec squared, we get tan x minus 2. Integrate e to the x. Okay, so the power stays the same. E to the x. Divide by 1 again, so it doesn't change. Remember, if you differentiate e to the x, you just get e to the x. That's what's so special about it. So if we integrate e to the x, we also just get e to the x plus c. I'm going to take a little detour from the handout. Let's just try one other question, which will illustrate the dividing technique, which is really important. So I'll make an extra one up. What about if we were going to integrate 4 sine 2x plus 1 over e to the 3x. Let's just try this one. Okay, you might want to pause it and have a think about that one before I go through it. So we've clearly got 2 separate functions that we're trying to integrate. Split the integral up. So that's 4 lots of the integral of sine 2x. Think about this one. We're trying to integrate 1 over e to the 3x. Now, I've not shown you a technique for integrating fractions. Like, say, you know, if we were differentiating a fraction, you might want to use the quotient rule. But just notice it's not actually a function divided by a function. It's just 1 over. We can just use index form, just the same as if it was like 1 over x cubed. We know that's the same as x to the power minus 3. So if it's 1 over e to the 3x, we could just write that as e to the minus 3x. Okay, so when we're integrating this, be careful, a bit more going on with this one. So sine integrates to minus cos. So I've got a 4 at the front. That's going to become a negative. value, so it's minus 4. Sine integrates to cos 2x, the angle stays the same. But because it is 2x, very, very important that we remember when we're integrating, we divide by the coefficient, which is 2. Okay, e to the minus 3x, so if I'm integrating an exponential, the power stays the same. The coefficient is minus 3, so I'm going to be dividing by minus 3. Obviously we need to tidy this up a little bit before we're finished, but we're almost done. So minus 4 divided by 2, that would equal minus 2 cos 2x. And I'd probably write this as, I wouldn't leave the minus 3 on the bottom. So that's minus a third e to the minus 3x plus c. Example 2. Given that a is a positive constant, might be important. We know a is greater than 0. And we've got this integral with limits. We're given an answer, which is quite a common exam style question. They might give you the answer and ask you to find another variable within your working out. Okay, so we know that this function here, if we integrate it between a and 3a, the answer would be ln 12. And we're being asked to find the value of a. So looking at what we're being asked to integrate, we've got a fraction, but there are two things on the numerator, and they're both being divided by x. Easiest way to approach this one is to actually split this up. You know, if you think about it, if you had 4 over 3, that's the same as 1 plus 3 over 3, which is the same as 1 over 3 plus 3 over 3, which is the same as 1 over 3 plus 1. You know, really important that we get our head around how fractions work even when there's algebra involved. If you have two terms on the top, they're both being divided by x. So we can split the numerator. We can't split the denominator, but we can definitely split the numerator, can't we? So I'm instead going to think about this as the integral of 2x divided by x plus 1 divided by x. So 2x divided by x is just 2. And plus 1 over x. Think about it as two separate integrals as well, if you want. It's not too bad, this one. I might keep it as 1. So if I integrate 2 with respect to x, it becomes 2x. Increase the power, so x to the 0, x to the 1, divided by 1. 1 over x becomes ln x. And the limits, which I'm going to use square brackets for, are 3a and a. I'm also going to think about the answer, which is ln 12. Because I'm going to have to treat this like an equation. Now that I can sub my limits in, I can rearrange and figure out what a would equal. So if we sub 3a into our first bracket, we're going to get two lots of 3a plus ln 3a, big bracket, minus subbing your second limit. So that would be, don't forget this bracket because we've got two terms, 2a plus ln a. All this is equal to ln 12. I've run out of space, but I'll tidy it up and set it back equal to ln 12. So let's see what we've got. We've got 6a minus 2a, so we've got 4a. Plus ln of 3a minus ln of a. And all of that is equal to ln of 12. So we're trying to rearrange this to figure out what a equals, aren't we? That's what the question says. So just find the exact value of a. I probably should have highlighted actually. Exact value of a means that we definitely don't want a decimal value. We're going to leave this as a logarithm for our answer. Okay, so you probably want to do this without a calculator really. As soon as you type stuff into the calculator, it'll just turn it into decimals. Look at what we can do here. Like, this is the key thing to focus on here, isn't it? We've got a log minus a log. So if you think about the log laws, when you're subtracting, if you combine them together, it becomes a divide. So we know that 3a divided by a is ln 3. and then we're nearly there. We just need to rearrange to figure out what a is equal to. So we've got 4a plus ln3 is equal to ln12. Similar, subtract ln3 from both sides, so now we've got a log minus a log, which becomes a divide, which is ln4. Okay, so 4a equals ln4. A would equal, divide them by 4. When you do this with the logs, you never actually see me writing it as all divided by 4. If you're dividing something by 4, write it as multiplied by a quarter. Because then it's a lot easier to think about. This coefficient in front becomes a power, because quite often if it's like a show question, the answer you get might not be quite exactly what, it might not look the same as what you're trying to get to, and you might think you've done something wrong, but you can just take it up to, as a power. This is not a show question, it just says exact answer, so I'm fine to leave it in that form. Okay, so next up is exercise 2. There's quite a lot of questions in there, guys. Use the word solutions. It's a really good exercise though to practice all these different techniques for integration by inspection. Once you've worked through those, the next thing that we're going to look at is a little bit more on integrating with ln. But first of all, practice all those key techniques that we've just looked at for the different inspection intervals. Obviously, if you need any help, just contact me or Johnny or Steve, and we'll be able to give you a bit more extra advice. Okay, thank you. Enjoy.